Alrighty, good morning, lads and ladies. Welcome back. You have made it through the first exam in MAP 2302, and hopefully you all still have your heads about you, which is a nice thing to be able to say after making it through a first test. Today we're going to do a handful of things. One of those things is going to be to talk perhaps a little bit about the test. If there's any particular problems from the test that you guys are especially distressed over, I would be happy to take a look at one or two of those. And then we're going to do something that I promised to not do pretty much for the rest of the semester, and that's look at some application problems. I am a mathematician, not a physicist, not an engineer. And as a mathematician, I think that this stuff is worth doing on its own for its own merits. It's fascinating just to kind of see the different ways calculus can take you when you start trying to glue calculus objects together. That's what differential equations is. But as you may know, one of the reasons differential equations is such a pervasive class, I bet the reason 9 out of 10 of you are here, is because you intend to go into some STEM related field, probably not the M, right? One of the STE related fields. And differential equations show up everywhere there. They are the kind of language that we use to describe physical phenomena, because that's just the most natural way to do it. They're things that evolve over time, things that change over time, related things that change over time. And that's differential equations. So today is the day for my engineer folks to get a feel for what sort of things they'll be doing. Also my physics folks. So kind of just to map things out, we're going to talk about models today. In fact, I'm not just going to talk about 3.1. I think I'm going to take a little bit of material from 3.2 also, just to kind of show you. It's more of an expository thing. Now, you will have some homework problems. Those will come from 3.1. Not going to give you any nonlinear modeling problems or any higher order DE modeling problems. But we're going to talk a little bit about how to take a real world situation and interpret it using differential equations, and then solve those differential equations to get some deeper understanding about the real world situation. The other thing we may do, if there's time, is explore a little bit the beginning of the discussion of general linear equations. And this is a big, big deal. So you notice there's only these 3 sections this week, and that's because this section is a monster. And then we'll move on to reduction of order, but that's not going to happen today. So 4.1 is probably going to take a couple days. We're going to spend a lot of time talking about linear equations in general, not first order linear equations, right? First order linear equations we've already solved. They're done. Integrating factors, worst case scenario, integrating factors, done. But the nth order general linear differential equation, those can be more complicated. I'm going to go into the theory on these. This is the place where I have to give you a little bit of linear algebra. We have to talk about some kind of heady things. But first, talk about the test, and then talk a little bit about linear models. So in order to do any of that, let me bring this up. Okay. I know that there are a few people who still need to take the test. I'm going to mention a few things about that too. What is today? Is it the 13th? Yeah. So today, we'll talk about the test. We are going to cover section 3.1, which is on linear modeling. And maybe a little 3.2. And we might section, well, might introduce the general linear equations. Which is section 4.1. We're a little out of focus there. Let's fix that. Okay, so 0 things, 0. Are there any problems from the test that you are just dying to see? Anything that bugged you? I know I had one person want to see the solution to the homogeneous equation that was in there. So I'd be happy to work that one out. Are there any other problems from the test that you really wanted to see?
I think for me it would have to be like the last part, where they gave us to choose either the homogeneous or the Bernoulli one. Can I see the homogeneous one?
Yeah. So that was the one. I actually had somebody else ask to see the homogeneous equation too. So we're definitely going to do the homogeneous equation. Is there anything else that you guys wanted to see?
Can we see number 11, the free response?
Okay. Anything else? Well, I guess two is probably about the right number. I don't know if we have time to do more than 2 test questions today. So I'll say this also about exam 1. If you missed exam 1, for any reason, you need to contact me about the makeup test. I'm only going to do 1 session of makeup testing. It will be during an office hour, either this Thursday or next Monday. The rule per the syllabus has to be within 1 week of the original test date. So I'm leaning towards next Monday right now, but if you got in a car accident or you were in the hospital or any of those classic excuses or non-classic excuses, or for whatever reason you missed the first test, I want you to take the test. I would much rather you take the test than get a 0. So if you missed the thing, reach out and I will put you on a list to take the makeup test. All right. Now the makeup test is going to be different from the previous test, but they have enough similarity that I don't want to reveal the whole thing here to those who haven't seen it. So I'm going to dip in here and write down the 2 questions we're going to look at. Of course, the problems will be different, but I don't want to give away too much. Well, no, we don't need to edit this. I guess we can do it. That's fine. All right, so we want to see the homogeneous equation, and we want to see number 11, which was so number 11, we're asking to determine if the function is homogeneous. Is that the one you wanted to see?
Yeah.
Okay. So I'll write these down. Okay. And our function there, I'll write this down. X squared plus y over x plus y squared sine of x over y is homogeneous. Funny that the 2 questions we want to see have to do with homogeneous functions or homogeneity. And the homogeneous equation that I ask you to solve, or that you had the option to solve, you could choose between the Bernoulli or the homogeneous. Y dx equals 2 x plus y dy. Okay. So in brief, here are the 2 problems. Determine if this function f of xy equals x squared times the cos of y over x plus y squared times the sine of x over y is a homogeneous function. And if so, state the order. And then the second one was to solve the given homogeneous equation, y dx equals 2 times x plus y dy. So here I tell you this is a homogeneous equation, just ask you to solve it. It's a homogeneous differential equation because the two functions m and n are homogeneous of order 1. And then in this guy, I just want to know, is this a homogeneous function? There's no equation to solve, just want to know, is this a homogeneous function? So how do you figure out if a function is homogeneous? This is something we've talked about. Let me pull the cam back up, sorry. All right, so we want to know, is this a homogeneous function? And if it is a
Yes.
homogeneous function, what's the order? And we want to solve this homogeneous equation. Was it Ross who was going to tell us? How do we determine if a function is homogeneous?
We need to make f of tx and ty,
Yeah,
and see
Yeah.
the form. We have to have the form t to the n times f to xy.
yeah, exactly. We want to scale these variables by the same factor. We want to kind of zoom in by a factor of t on the input space. So we're going to look at f of tx comma ty, and then see if when we do that, we can factor some power of t out and get the original thing left over. So remember, f of xy is homogeneous, means f of tx comma ty is equal to t to the alpha times f of xy. You could use an n there instead of an alpha if you wanted, that's fine. The idea is some power of t should come out. Let me get a better purple pen. Okay. So here, f of tx comma ty is tx squared times the cosine of ty over tx plus ty squared times the sine of tx over ty. So everywhere there's an x, I swap it for tx. Everywhere there is a y, I swap it for ty. That's what this notation means, right? Function notation. And now I'm going to try to simplify and see what I get. There are a few places where I'm thinking you can see some nice things happening. For example, in here, these t's will cancel. And then here, tx squared is t squared x squared. So I have t squared x squared cos of y over x plus t squared y squared sine of x over y. And now I have these two terms, right? This is multiplying, so this is really one term. This is multiplying, so this is really one term. So I have this big first piece and this big second piece. Both of them have the common factor of t, t squared. So I can bring a t squared out, and what's left is x squared cos of y over x plus y squared sine of x over y. So out comes this t squared. And what's left over when I do that is my original function. So yeah, this is homogeneous. This is t squared times f of xy. So yes, f is homogeneous. Of order of equals 2. All right, so that was that one. Yes, this function is a homogeneous function, and the order is 2. The algebra steps to get there are not that bad. Any questions on this one? Okay, the next one was to solve this homogeneous differential equation. Solve solve the equation y dx is equal to 2 quantity x plus y dy. And you have a choice here. As with all homogeneous differential equations, you can choose to substitute like x equals uy or y equals vx. It's your choice. It's your choice. So I chose to substitute x equals uy. Right, the idea is you scale one of the variables, just one of the variables. And that's because both of these functions are homogeneous functions. When you do that scaling, things come out nicely. So you can let x be something new times y, or you could let y be something new times x. Either way, either way. And I think that's the notation your book used, right? Make sure it is. They write ux and vy, or do they do it the other way? Let's take a quick look. Oh no, they were writing x equals vy. Okay, let me write it like that. I don't want to confuse you. Okay. It really doesn't matter. You could write it either way. When I solved this, I wrote it the other way. So if you're going to make a substitution in a differential equation, you need to know how to relate the old differentials, the dx, to the new differentials, the dv's. And so this guy, you calculate dx using the product rule. This is v dy plus y dv. And then we plug this stuff in here. So everywhere there's an x, I'm going to write v times y. And everywhere there's a dx, I'm going to write v dy plus y dv. So the equation becomes I've got my y times dx, which is v dy plus y dv. That's the left-hand side. Equals 2 times, and then I've got an x here, so that's vy. Y just stays y, and dy just stays dy. So the goal is to rewrite the whole differential equation in terms of, without any x's, in terms of just the variables v and y. And that's what we've done here. There's no x's or dx's. Now I'm going to regroup this, and it should become a separable equation. That's the idea. Remember, homogeneous equations, when you make this substitution, should become separable. All right. Well, on the left-hand side, I've got y times v dy. And then I've got y squared dv. And on the right-hand side, I've got 2vy dy plus 2y dy. And now I collect up all my dy and dv stuff. So which side do we want to have the dy's on? I guess I can pull everything to the right-hand side. So I've already got these two over here. Honestly, I could have left these like this, but I'm going to combine with this term. So I think it's useful to leave it like that. So I'll keep the y squared dv on the left. And then on the right-hand side, I've got 2vy plus 2y minus yv, which is the same as vy. So this is just going to be, I'll write it out, why not? So this is 2vy plus 2y minus yv all times dy. And these two are like terms. Vy and yv are the same thing. So this is y squared dv equals 2vy minus yv is 1vy plus 2y dy. And the hope is that this is separable now. Does anybody see how to separate variables here?
You can factor out a y on the right side.
Very good. The right-hand side, this vy plus 2y has a common factor of y. So I get y squared dv is equal to y times v plus 2 dy. Alrighty, so now I'm going to divide both sides by y squared, divide both sides by v plus 2, and you get 1 over v plus 2 dv is equal to y divided by y squared is 1 over y dy. And that means we can integrate. So the integral of 1 over v plus 2 dv is equal to the integral of 1 over y dy. Hence, the integral on the left-hand side here, this is a tiny little substitution if you like. I think everybody at this point knows that that's the natural log of v plus 2. And again, I'm eschewing the absolute values. Yes, if we're being super careful here, we'd want to use absolute values and pay attention perhaps to some domain. But just assuming everything is positive. And on the right-hand side here, I have a natural log of y. And I need to fudge a plus c somewhere, so I'll put it here. Now we're almost done. We're almost done. What do I still need to do?
Reverse the substitution.
Yeah, very good. So my original equation asked about x's and y's. I've given a solution here in terms of v's and y's. So if we look back at our substitution, since x was equal to vy, we know that x over y is equal to v. So this is the natural log of x over y plus 2 equals the natural log of y plus c. And I'm thinking it may be possible to get an explicit solution here if you want it. Well, maybe not, no. Yeah, I was thinking if you had a common denominator here and then peeled off the log y term, but you'd have an x plus 2y over y inside this log if you did that. So this is as good as you can get. You cannot get an explicit solution here, not nicely. Not that I see at the moment anyway. If we try to exponentiate on both sides, you'd have this equals y times e to the c. Yeah, no, this is good. So you get here and you're done. All right. So those were the two problems on the test having to do with homogeneity. They went quickly enough here that if you have any other burning questions from the test, I'd be happy to take one more. Let me go grab some coffee. I'll be right back. Okay. Anything else from the test beating us up? Keeping us up at night, taking up our shower brain
I
time.
think it was the last question about Bernoulli's equation.
You want to see the Bernoulli equation? Sure.
Yeah.
So my advice for Bernoulli equations, although it's not in the book, is always to divide through by y to the n. That makes it just easier to see what's going on. Again, I'm going to turn off my share while I grab the equation. So it's dy dx minus y equals e to the xy squared. And we solve. Okay. So this is already in the standard form of a Bernoulli equation. We've got y prime plus p of x times y equals q of x times y to the n. So this is Bernoulli with n equals 2. And my advice is to begin by dividing both sides by y to the n. So I'll use my if and only if notation. This would be 1 over y squared times dy dx minus 1 over y equals e to the x. The reason I do this is because the substitution you're going to make is kind of easier to make into this. Namely, what you're really subbing for is what this middle piece becomes. The way the book says it is you sub u equals y to the 1 minus n, which in this case is y to the 1 minus 2. So you're subbing u equals y to the negative 1, which is 1 over y. And just like in any other differential equation, when you substitute, you need to substitute for the relevant derivative stuff. So in addition to that, we need du dx, which here is going to be negative 1 times y to the negative 2 times dy dx, i.e. du dx is equal to negative 1 over y squared times dy dx. And again, I hope that you can see why that's nice to write things in this way, why it's nice to divide through by y to the n. Here you have 1 over y squared times dy dx, and over here you have negative 1 over y squared times dy dx. So you see that this piece is negative du dx. This piece is u, so this is minus u. And then the right-hand side just stays e to the x. And the miracle of this substitution is that you go from a nonlinear differential equation to a linear differential equation. I can multiply both sides by negative 1 and rewrite this as du dx plus u equals negative e to the x. And then we're going to solve this linear equation. If it were separable, we would solve it by separating variables. I don't believe it is separable. No, it's not. So we need to use integrating factors. So my mu, my integrating factor, that's always e to the integral of p of x dx. Here, p of x, rewriting it in this way, p of x is just 1. So this is e to the integral of 1 dx, which is e to the x. Because p of x is 1. P of x, remember, is the coefficient of the non-differentiated term here in standard form, standard linear form. So my equation becomes e to the x times du dx plus e to the x times u equals negative e to the x times positive e to the x is negative e to the 2x, right? E to the x times e to the x. That's e to the x plus x, if you want to think of it that way. Or it's e to the x all squared, which is the same as e to the 2x, whatever algebra rule helps you with multiplying like bases. And the left-hand side, we can now interpret as a product rule derivative. The right-hand side is what it is. So this left-hand side is the derivative of e to the x times u, right? This is like leave e to the x alone, differentiate u, plus differentiate e to the x, get e to the x, and leave u alone. So this whole left-hand side here is equivalent to, there's a bunch of ways to say this. What I've been writing for you in class is e to the x times u all primed. And that's equal to negative e to the 2x. So if I want to undo the prime on the left, because it's not so nice to write in Leibniz notation, you can call it d this thing over dx if you wanted to, and then separate variables, but it looks weird. If you want to undo the prime on the left to help you solve for u, that's our goal, is to find the function u. You integrate on both sides. So e to the x times u is equal to the integral of negative e to the 2x dx. And the integral of negative e to the 2x is negative 1/2 e to the 2x plus a constant. And now I divide through by e to the x to get u alone. Therefore, u is equal to, if I divide through by e to the x, e to the 2x divided by e to the x is e to the x. So I get negative 1/2 e to the x plus c divided by e to the x is c times e to the negative x. And that's your solution in terms of the variable u. But just like in the other problem, since we made a substitution, we need to go back. U is 1 over y. And if you wanted to stop here and say that this is the implicit solution, I would accept that. That's fine. If you wanted to take reciprocals on both sides, you can do that. That's fine. Bunch of ways to do it. You could say, or y is equal to plus c to the x, all to the negative first. Just remember that when you take reciprocals, because these are being added, you can't take the reciprocal of each piece on its own. You need to have a common denominator and kind of go through that whole thing. So it's a little bit of a chore to deal with this. You cannot distribute this power, in other words, right? Power is never, ever, ever distributed over addition or subtraction. So you could stop here. Or here. Or you could simplify further. But you can't distribute that power. Can't distribute the negative power. So if you're going to simplify further from here, you have to rewrite each of these as fractions, have a common denominator, put the two fractions together, and then take the reciprocal. That will work. Okay. So I think that's enough from the test. Like I said, I'll be writing a makeup test. If you missed this test for whatever reason, then I want you to take the makeup test. I have had a few people reach out to me for various reasons, and they'll be taking the makeup test. If anybody else is here today who missed the test, I strongly encourage you to reach out to me and let me know that you need to take the makeup. I'm going to put you on a list, and then I'll post an announcement a little later in the week letting you know when the makeup will be. So I'm hoping to talk to each of you individually to make sure that the makeup is scheduled for a day and a time when you won't have to like miss work or anything. All right. So I'll tell you my rule for grading tests. I'll always get them back to you within about a week. It's very rare that it takes me more than a week. Sometimes it does. The department is supposed to be buying me an iPad, which should help me grade things faster because I don't have any touchscreen devices here at home large enough for me to grade on. I've been using the mouse to make comments on your study guides, and that's incredibly tedious. So should be able to get those back to you reasonably quickly. So the next thing we're going to do is talk about linear models. Maybe a little about non-linear models, but primarily linear models. There are some linear models that you're already familiar with. You might not have known they were linear models, but they are. So this is section 3.1. Modeling with linear models. The most famous and most important linear model is one where the evolved state of the system is proportional to the current state of the system. So when we discuss differential equations in the context of modeling, we're always talking about the evolution of some system or object over time. We're talking about how something changes, almost always over time. So the sort of classic one is where the rate of change for the system is proportional to the current state of the system. So your book has a name for this. They just call it growth and decay. In many systems, population, radioactive decay, etc. The rate of change for the measured quantity is assumed proportional to that quantity. I'll give you just one moment. I'm going to let my cat in. So the classic example here is a population, right? If every person, or let's not say person because people reproduce in couples, but if we're talking about something like bacteria or things that reproduce asexually, if every object or critter, when I was use the word critter, if every critter has 10 kids every generation, then the number of kids each generation, the rate of change can be measured relative to the number of things that are there. So the classic example is a bacteria that splits, right? If each bacteria splits in two, then the rate of change of growth for that population of bacteria is going to be equal to 2 times the number of bacteria that are there right now. So the way we express these usually, they're using variables x and t here. So x is the quantity being measured, and t is understood here to be time. Then these situations are described by dx dt is equal to some constant k times x. So again, in the situation I was describing a second ago, where every unit of time, each object in the measured quantity splits into k objects, you would have this thing, right? K is a constant. And this is not an exciting differential equation. I just want to say at the outset. Usually when we think about these things in the real world, they come with some sort of initial conditions. X of t0 equals x0. So, I tell you at some certain time, the population is this. And then I ask you to solve this differential equation subject to those conditions. You've seen lots of this in your life. You've seen this as far back as like college algebra. If you've been taking math here at Santa Fe, we just didn't really tell you. When you learned about half-life, doubling time, exponential growth and decay in those algebra classes, this is what's going on in the background. And that kind of gives away what's going to happen. But we can look at an example. So, for example, I've got some bacteria. The bacteria population at time t equals 1 is P0, sorry, at time t equals 0 is P0. And at time t equals 1 is P1, which is equal to, we call it 3/2 P0. Okay, so we're told that we've got some initial population of bacteria, some amount of bacteria that are there at the start. That's P0. And then 1 hour later, these are measured, time is measured in hours. Um, 1 hour later, you've got 1.5 times the amount, 3/2 times P0. They tell us that the rate of growth is proportional to the number of bacteria present at time t. And they want to find the time necessary for the number of bacteria to triple. So they say the rate of growth is proportional to the population find the time for the population to triple. All right. So here I'll use P for my population. P is kind of playing the role of X in this equation. It's my measured quantity. T, little t, will still stand for time. And I'm going to set up this differential equation. So because we are told that the rate of change is proportional to the population, the rate of change is dp dt, right? The rate of the change in the population over the change in time. That's how fast the population is growing. And we're told that this is proportional to, meaning is equal to a constant times the population itself. So I'm trying to identify the population function P of t. I've kind of been given some initial conditions. I'm told that P of 0, that's just P naught, but I'm not told what P naught is. I'm not told what that initial population is. I'm also told that P of 1 is 3/2 P naught. So this is kind of the best I can do. This is the most I can say in terms of differential equations from the paragraph given. You notice it has a handful of unknown constants. I don't know what K is. I don't know what P naught is. But I do know how to solve differential equations like this. How do you solve this differential equation? Oh, kitty. Is this not a cat? She cray cray? Is she sweet? How do you solve a differential equation like this?
You can separate the variables.
Yeah, it's separable. So we're going to jump in here and separate variables. Where'd I go? There we go. Okay. Separating variables, we get dp over p is equal to k dt. And then integrating on both sides, the integral of dp over p is the natural log of p. And the integral of k dt is kt, which means, oh, sorry, kt, ooh, shit, plus c. Gotta have that constant. So this means that p is equal to e to the kt plus c. And that's the same as e to the kt times e to the c. And what I'm going to do is I'm going to relabel this e to the c as something else. Doesn't really matter what you use. Let me just call it C2. So solving the differential equation, we find this. I'll write it in function notation. P of t is equal to C2 times e to the kt for some constants C2 and k. All right. Now, I'd like to do a few things if I could. I'd like to identify the constants C2 and K. The best I can really do, we know that P of 0 is equal to P naught. That's one of our initial conditions. really it's a boundary condition. It's one of our two boundary conditions. This is going to give me C2, means that P of 0, which is C2 e to the k times 0, is equal to P naught. E to the k times 0 is e to the 0, that's 1, so this is just C2 equals P naught. So P of t is really P naught times e to the kt. And this is probably something you've seen before, again, as early as like college algebra or algebra 2 in high school. The other bit of information I have we know that P of 1 is equal to 3/2 P naught. Which tells us if I take my function and I plug in 1 for t, I should get 3/2 times P naught. So I'll write it like this. P naught e to the k times 1 is equal to 3/2 P naught. I can divide both sides by P naught. E to the k times 1 is what's left on the left-hand side, which is just e to the k. So e to the k has to be equal to 3/2. And this is an equation I can solve for k. If you take the natural log of both sides, you get k is equal to the natural log of 3/2. And I would just leave it like that. Therefore, you now have full information about the function p. It's equal to whatever that initial population is. We don't know. We don't have information to get it, but it's P naught times e to the natural log of 3/2 times t. Now, the truth is, and I don't believe your textbook does this, but the truth is you can actually simplify this function quite a bit. I can write this as t times ln of 3/2. Then I can bring the t inside. So this would be e to the ln of 3/2 to the t. So let me go ahead and just show you what this looks like, because the algebra steps here are quite nice. Okay, this is just commutativity of multiplication. Something times t is the same as t times that thing. And then this is P naught e to the ln of 3/2 to the t. And then that e raised to the natural log of something is just that thing. So this is 3/2 to the t. Now you could just leave your function like this. There's no harm in that. But I think we'd all agree that this is nicer in some ways, right? The base is no longer a natural exponential. So in that sense, this isn't nicer, but algebraically, it's just got fewer bits in it. The last thing we were asked to do is answer how long is it going to take this population to triple? So are there any questions so far? This is us solving the differential equation as thoroughly as humanly possible. Finally, the population triples. The population has tripled. When P of t is equal to 3 times P naught. That's what tripling means. It means it's gone up by a factor of 3. The original population is P naught. So if you're tripling from the original population, that means your new population is 3 times the original, 3 times P naught. Which is equivalent to saying P naught times 3 halves to the t is equal to 3 times p naught. Again, divide both sides by p naught. We get 3 halves to the t is equal to 3. Take the natural log of both sides. The left-hand side becomes t times the natural log of 3 halves. So the time to triple is, now we divide both sides by the ln of 3 halves. We get the ln of 3 divided by the ln of 3 halves. And there isn't any simplification that you can do here algebraically, really. You certainly cannot cancel ln's, you can't cancel the 3's, you can't combine these, not in any clean way, not using any rules for logarithms. The only thing that you could apply here is the change of base formula. That's not useful. So if you wanted to know that time, you would have to resort to some sort of calculator. I'm going to have an emulator here for fire. Emulator for the TI-84. So let's see if she shoots. So what we need is the natural log of 3. Natural log of 3 halves. About 2.7 hours. And when you think about it, it's remarkable that we're able to do this given how little information we were told at the start. We were told that the rate of change for the population is proportional to the population itself. That's all. And we're given what are called boundary conditions, 2 values of the function p. Not even explicitly, right? Just in terms of the constant p naught. So with remarkably little information, we were able to tell how quickly this population will triple. And of course, there's nothing sacred about the number 3. If you wanted to know how long this population to quadruple or sextuple or whatever, you can cook that up as well. The differential equation solving here is only a small part of it. Most of this is algebra, and that's why you've seen problems like this in college algebra and pre-calculus. But this is just one example, and I want to draw your attention back to the initial concept, which was that for many types of growth or decay situations, the rate of change for the measured quantity is proportional to the quantity itself. Anytime your quantity is made up of individual things that split up into more copies of themselves, or that kind of decay in that same sort of way, where each little unit decays by a certain percentage each time, you'll be looking at a situation like this. And the classic examples are the classic examples. Populations of all sort, as long as they don't have any limiting factors from the environment. Like here, this bacteria population, this might work really great for a few hours, but eventually the petri dish is going to get full, it's going to get crowded, and that shit won't work anymore. Obviously, the population can't go to infinity. The function p of t here, if you graph this function, no matter what you choose for p naught, this will eventually go to infinity as t gets larger and larger, and that's not realistic. We know populations can't go to infinity. So there are limitations on this model, and we'll talk about that when we talk about some nonlinear modeling stuff. But under reasonable circumstances, if you have a population that isn't limited by its environment or by something hunting it, then usually they'll grow exponentially. Spread of viruses works like this really well. You may have seen the exponential curves that were all over the place at the start of COVID. So many other things. And why is that? Because the rate of change for the spread of COVID, right? How many people have COVID is proportional to the rate of change of how many people have COVID, right? How many people are going to get COVID today is proportional to the number of people that have COVID today, because maybe each one of those motherfuckers coughs on 2 people, right? So there's many, many, many things in the world that work this way. Single most important model, but mathematical model, not just in differential equations, but anyway. What else to say? If you come back to the differential equation, come back to the ODE we started with. If k is not constant, if k perhaps depends on t, this may or may not be separable. If k depends on t and p, then this definitely likely isn't going to be separable. So sometimes if k is a constant, if your population is a rate of change is proportional, like proportional in terms of a constant, that's what proportional usually means, to the thing itself, then yeah, then this is always going to be separable. But sometimes this k here could be a function of time, could be a function of time and population. So in certain circumstances where this logic still sort of holds, you need to think a little bit more carefully about how to solve the differential equation. You're not likely to run into anything like that, but just a word to the wise. I'm not going to solve a half-life problem. I don't want to bore you guys. It's the same as it was in high school, same as it was in college algebra, same as it was in pre-calc. The only difference is you start off by solving a simple separable ODE. What I do want to talk about are temperatures. So you've got 2 half-life examples in your homework that you'll see, but the next kind of exciting model Newton's law of cooling. And the basic idea there is that if I have something like a cup of coffee sitting on my desk, where the coffee is much warmer than the surrounding environment, then the rate at which the coffee will cool is proportional to the temperature gradient. So the big idea, the rate at which an object will cool, assuming the object is warmer than the surrounding environment, is proportional to the temperature difference. And this might sound like a really simple concept, but it's actually a little bit subtle, because that temperature gradient, that temperature difference itself is non-constant. As the coffee cools down, the difference between its temperature and the temperature of the room changes. So it's not the case here that you're looking at a constant. It's not the case that, that the rate of change is constant. So the notation your textbook uses to describe this is that d temperature, d time, the rate of change of the temperature over time, is proportional to, so is equal to a constant times the current temperature minus the ambient temperature, which they call, for whatever reason, Tm. So where K is a constant and Tm is the ambient temperature. So this is something Newton discovered empirically. He didn't derive this from first principles. It's not like this is a consequence of F equals ma or anything like that. He just did some measuring, right? He just measured the rate at which a few things cooled down when he put them in a room where he could measure the temperature. And he discovered that this equation seems to hold just by making tables. All right. This is also a linear first order equation. And we can work a quick example here. Maybe I take a cake out of the oven. And the oven was, the cake was baked at 300 degrees. So I take a cake from the oven at 300 degrees Fahrenheit. And we'll get another boundary condition. We'll say, and 3 minutes later, use the numeral, 3 minutes later, the cake is 200 degrees Fahrenheit. If the ambient temperature of the room is 70 degrees Fahrenheit, how long will it take the cake? Wait, no, they give us the ambient temp. How long will it take the cake to cool off to 70 degrees if the room temp is 70 degrees? Okay. That's an odd question. This is really the way your book phrases it? Yeah, okay. How long for the cake to cool? To room temp of 70 degrees Fahrenheit. Before we begin this, I'd like to have a little discussion. What do you guys think? Thinking about mathematical models in general, let me bring this back. Thinking about mathematical models in general, thinking about the differential equation that we just solved, which is pretty similar to this one, and the fact that the solution to that curve, or the solution to that equation was an exponential. What do you think the answer is going to be here? Let me put this another way. You've all held hot things, and you know that they cool down over time, but do they ever actually reach the room temperature?
No.
No, they don't. It would take an infinite amount of time for this to actually reach room temperature. If you think about it in terms of kind of the fundamental concepts behind heat, the intensity of the random Brownian motion of the atoms inside, you know that they're going to relax. They're going to stop moving more and more and more. They're going to chill out over time. But for it to reach exactly the room temperature would in theory take infinite time. So the answer to this question, we can answer qualitatively without even doing any analysis. It will never happen. It would require infinite time. But we could say, how long would it take to get to 71 degrees? You give me any 70 plus epsilon, and I could give you an exact amount of time to get there. So I'd like to also play around with that a little bit. But first, let's focus on solving the differential equation. So our function capital T is a function of time, and we're given some boundary conditions. Let's go ahead and plug in the information we have to the differential equation and see what we get. Newton's law of cooling states that d big T over d little t is equal to some unknown constant k times big T minus the ambient temperature. And I'm going to leave units off here because mathematician, not physicist, sorry. Not sorry. So we have this differential equation. We'd like to solve it for the function big T. Any ideas how we could do that?
Separate the variables again.
Yeah, again, this is separable, right? Here is a pure function of big T, and here is a constant. You could think of that as a function of little t. So if I separate variables, I get d big T over big T minus 70 is equal to k times d little t. And integrating on both sides, we get the natural log of big T minus 70 is equal to k times little t. Or big T minus 70 is equal to e to the kt, which we can rewrite as big T of t. I'll write it like this in the function notation, is equal to e to the kt plus 7. Now, temperature here is measured in degrees Fahrenheit. Time here is measured in minutes. They gave us the units. So it's implicit. I'm not going to say that in the notation down below. Just like with the previous problem, I can use the given boundary conditions to try and sort out the constant k. So I know that when little t is equal to 0, the moment I take the cake out of the oven, it's 300 degrees. And I know that 3 minutes later, the thing's down to 200 degrees. So we have 2 bits of information we can use here. We know that T of 0 is equal to 300 and T of 3 is equal to 200. Plugging in 0 for T here isn't really going to teach me anything. Oh, did I leave off a constant when I integrated? I did, didn't I? Shit, I'm so sorry. Bad habits, bad habits. Let me come back here. This needs a plus C. Yeah, so there would be a plus C here. Sorry about that. So what we have is T equals e to the kt times e to the c plus 70. And then again, this e to the c I'll relabel as C2. So big T of little t is C2 e to the kt plus 70. Yeah, okay, sorry about that. Make sure you come back to this line and add your plus c here. I got sloppy. Then when you exponentiate to undo the logarithm, you'll have e to the kt plus c on the right-hand side, the plus c in the exponent. Splitting that up, that's e to the kt times e to the c, and then we relabel e to the c as C2. Okay, so now this T of 0 equals 300. This will get us some information. That'll help us find C2. And the T of 3 equals 200 will help us find K, given that we already know C2. So this piece is going to tell me that C2 e to the kt plus 70 is equal to 300, which means that C2 e to the kt is equal to 300 minus 70, that's 230. I'm just going to tuck that in my pocket. Oh, sorry, I plugged in 0 for T. I'm sorry, my brain is just not playing nice. And e to the k times 0, that's e to the 0. So that's the same as just saying C2 is equal to 230. All right. So we plug in 0 for T, and we set that equal to 300. That's using this information. E to the k times 0 is e to the 0, which is 1. So this piece is just c2 times 1. So c2 is 230. Now I can use this other boundary condition to solve for k. We have, let me update this. We'll write it like this. So big T of little t is 230 e to the kt plus 7. That's where we are so far. And using the fact that T of 3 is equal to 200, we're going to solve for K. So T of 3 is 230 times e to the k times 3, or e to the 3k plus 70. That is T of 3, and that should be equal to 200. So I have now an equation I can solve for k. If I subtract 70 from both sides, I get 230 e to the 3k is equal to 130. Dividing both sides by 230. Divide both sides by 230, you get e to the 3k is equal to 13/23, which means take natural logs of both sides, you get 3k is equal to the natural log of 13/23. So k is 1/3 ln 13/23. Everybody with me here? I know things got a little bit wonky at this point, so I'm going to give you a second to make sure your notes are clear. After we separate variables and integrate, so from here, when we separate our variables, we integrate on both sides. The left-hand side becomes the natural log of t minus 70, and the right-hand side becomes kt plus c. And I left that plus c off when we first did this, so please make sure you go back and add that plus c. That means that your temperature function, big T, is equal to some constant times e to the kt plus 70. And that first constant comes from this plus c that you get from your integral, right? E to the kt plus c is e to the kt times e to the c, and we relabel e to the c as c2. You can just call it c again if you really wanted to, but I don't like to overload the variable c. And from there, now that we have this, we can plug in our boundary conditions to solve for the two unknown constants, C2 and K. Plugging in t equals 0 lets us solve for C2. Plugging in t equals 3 lets us solve for K. So now I have full information about the function. And so our temperature function is T of t equals 230 e raised to the 1/3 natural log of 13/23 times e plus 7. This exponential here, growing or decaying? Why?
Decaying because the natural log is equal to a negative number.
Yeah, good. The inside of this natural log 13 over 23 is smaller than 1. And when you feed the natural log function an input smaller than 1, you get out a negative number. So this is e raised to the 1/3 times something negative times t. That's e to the negative something times t. So the exponent here is negative, which means this is a decaying exponential. It's not an uncommon thing here to approximate these. So if I wanted to, the natural log of 13/23 all divided by 3, that's negative 0.19. So this is approximately 230 times e to the negative 0.19 t plus 7. That sort of intuition, knowing that this is going to be a decaying exponential without doing the calculator thing, is important, right? So the observation that Maxwell made, that this exponent is negative, is a valuable one. So remember the argument here, the natural log term is negative because 13/23 is smaller than 1. All right, they asked us how long until the temperature is exactly equal to 70 degrees. Well, if t equals 70, if and only if 230 e to the 1/3 ln 13/23 t plus 70 equals 70, which is equivalent to saying that this exponential is 0. Which never happens. Bunch of ways to think about that. You know that exponential functions are never 0. Right? You divide both sides by 230 if you want. And say, okay, this goes away, and then you need this piece to be 0. But you know, yeah, e to some stuff, that's never 0. There's no real number, no, not even any complex number such that e to that shit is equal to 0. However, right, because e to some shit equals 0 never happens. However, as t goes to infinity, 1/3 ln 13/23 times t goes to negative infinity. So then t to infinity, 230 e to the 1/3 ln 13/23 t. This limit is 0, i.e. the cake is a lie. The cake approaches room temp as t goes to infinity. Now, if you gave me any temperature above 70 degrees, 70 plus epsilon, 71, 70.001, we could find a definite solution, right? It would just boil down to this thing is equal to whatever temperature greater than 70 it is. If you don't know how long to get to 71 degrees, this would be a 1, and then you would solve that equation for t using logarithms. So this is Newton's law of cooling, and it's not an exact thing. There are many situations in which this breaks down. If the temperature gradient is very, very large, then things actually cool faster. If the temperature gradient is very, very small, then things cool a little bit slower. But Newton's law of cooling is an empirical rule. It's something, again, he came up with just looking at experimental evidence, experimental data. And it's pretty good. It works pretty well for most human scale and human temperature things. So if I wanted to know how long is it going to take my coffee to go from 190 degrees down to 120 degrees in a 70-degree room, it'll be really good at that. The constant K involved in Newton's law of cooling depends on the thermal conductivity of the material that's cooling. It depends on the container you're in. It depends on any sort of convection that's going on. That constant K is actually really sensitive to the environment. If you have fans, for example, blowing on your cup of coffee, it will cool down much, much faster. If you have an oscillating fan, then K is no longer a constant, right? Just like we talked about in the previous model, K doesn't necessarily need to be a constant. But in these simplified models, it's generally assumed to be one. Questions on this or the last example?
Professor, what did you put e to the when it says which never happens because
This is e to some shit. Just the word shit, S-H-I-T.
okay.
Sorry. Okay. Let's see. We can do the mixture problem. I don't really like that one. We could do the LR circuit. I don't really like that one either. So the other two examples that I'm like torn between from this section of the textbook are both kind of silly. LR circuits are a thing, but how many of you have taken physics 2? Taken or are taking physics 2? You can give me a hand raise or whatever, so any react in Zoom, just to show me. Try to keep it up for a second. Taken or are taking physics 2. Considerably less than half. So I'm not going to do the LR circuit because odds are you don't, unless you are familiar with physics 2, you don't know what inductance is, and all of that stuff would be quite complicated. So we're going to do the mixture problem. Suppose I have a tank of salt water. I'm adding water. I'm adding more saltier water. And at the same time, letting the tank drain. So this is like a system where you have an input and an output, and you see these things all over the place. Think water treatment plant, think poop instead of salt, right? You've got those big settling tanks. You've got all sorts of situations in the industrial world where you've got things coming in and coming out. You've got some solution coming in and some solution coming out, and maybe the solution coming in is more dense with stuff than the solution that was already there, or vice versa. So what you have here are a concentration gradient. There's a differential equation to describe the concentration of the stuff going out, and we're going to cook that up. Let me draw for you a little picture. Here's my tank. Here's a nozzle letting some stuff in. And maybe over here, I've got a nozzle letting stuff out. Again, all sorts of physical systems in the industrial world work this way. Suppose that this is again salt water, and that the rate of stuff coming in is the same as the rate of stuff going out. So there's a constant 300 gallons in here. Suppose that the stuff coming in has a higher concentration of salt than the stuff going out. I'm going to let A of t be the amount of salt in pounds in the tank, in all the water in the tank. Okay. So dA dt is the rate at which the amount of salt is in the tank is changing. Suppose I'm bringing 3 gallons a minute of stuff in, and I'm letting 3 gallons a minute out. It's necessary that the inflow and outflow rates are the same if the amount of water in the tank is to remain constant. If the concentration of the stuff coming in, well, let me say this. So then dA dt, before we talk about that, dA dt, the rate of change of the amount of salt in pounds that's in the tank is equal to the input rate of salt, input, minus the output rate of salt. We'll call these R in and R out, respectively. The rate in and the rate out. My goal here is to set up a differential equation for the amount of salt that is currently in the tank, because the amount of salt that's currently in the tank is maybe important to my machinery. Maybe I can't allow the amount of salt in the tank to go over some constant, or my machinery will start to rust or something like that. All right. So let's assume that the amount of salt in the stuff that's coming in let's assume that the concentration of the salt coming in and the inflow is 2 pounds per gallon. And let's assume that the stuff, okay. Yeah, no, okay. And let's assume that originally there's 50 pounds of salt dissolved in the 300 gallons. I would like to set up and solve the differential equation that tells me how much salt there is in the tank at any given moment. The big idea here is that this dA dt is R in minus R out. And then this initial condition is going to allow me to determine exactly the missing constants. So what I need to know is what is R in and what is R out? The rate at which salt is coming in is the concentration of the salt coming in times, or the concentration of the solution coming in times the rate at which the stuff is coming in. The water, the flow is coming in. So R in, this is equal to the concentration times the flow rate. Right? How much salt is there in each unit of the fluid times how much fluid? Well, the concentration of the stuff coming in is 2 pounds per gallon. And then the flow rate, the rate at which the fluid is coming in, is 3 gallons per minute. And what you see when you do the dimensional analysis here is that you can cancel the gallons and you get 2 pounds per minute. I'm sorry, 3. You got 2 times 3, 6 pounds per minute. I'm sorry. But the big deal is that the units cancel. So you've got your rate at which salt is coming in, just the salt, is 6 pounds of salt per minute. What about the rate at which this stuff is going out? How fast am I losing salt? Well, again, it's the concentration times the flow rate. But here the concentration is a little trickier to figure out. The flow rate, I know I've got 3 gallons per minute coming out. But what is the concentration?
It's the 50 pounds divided by the constant 300 gallons in the tank.
Almost. So my original concentration, there's a lot of wisdom in what Maxwell just said. Did everybody hear what Maxwell said? He said, we're going to take the quantities here and divide them. Now, concentration is we would say that there would be originally 50 pounds per 300 gallons. That's true. But I want, this should be sensitive to time, right? Because that concentration of the salt flowing out isn't the same all the time. I'm putting saltier stuff in than I started with. So this concentration is going to depend on the amount of salt that's in there at any given time. Now you're right that if I wanted the initial concentration, I'll take the initial amount of salt and divide by the volume of water that's in there. If I want the general concentration, if I want to know what is the concentration at any given moment, I should take the amount of salt in that moment and divide by the amount of water in the tank. Is that clear? By the volume of the water in the tank, volume of the solution. So the big deal is that this amount of salt in the tank is changing. It starts at 50 pounds, but it's going to be going up because I've got saltier stuff coming in. So my concentration here is the function A of t divided by the volume of the tank, which is 300. And again, this is pounds per gallon. And then the rate of outflow is, again, 3 gallons per minute. So what we end up here, again, you can kind of cancel the units of gallons. You have A of t over 300 times 3. So that's A of t over 100 pounds per minute. And this is a little bit subtle. So I want you to take a second and make sure you're comfy. The big deal is that the concentration here, this is equal to the amount of salt in the tank, divided by the volume. And because the amount of salt is the thing I'm trying to track, it's the function A of t, it changes over time. Rather than just using the initial amount here, I want to use the function A of t here because I know that that concentration is changing. Now, a quick comment. You could adjust either of these flow rates to be non-constant or constant and different from each other. All of those things are possible. I could say the flow rate is going to be sinusoidal. It speeds up, it slows down. I could say that the flow rate out is faster than the flow rate in, so the tank is draining, and that will change the concentration function. I could say that the flow rate in is faster than the flow rate out, so the tank is filling, and that will again change how the concentration function works. All right, now we're ready to set up or write down our differential equation. dA dt is equal to R in minus R out. R in is 6. I'm going to leave off the units here. Minus the flow of the rate at which salt is flowing out, which is A over 100. And this is a differential equation that we can solve. Let's see, I think I am just about out of time here. So rather than burning up the rest of extra time, I'd like you to just tell me, how do we solve this differential equation? We've got some initial conditions. We know that A of 0 is 50. So the challenge in this section is setting up the ODE, right? All of these are things that we know how to solve from previous sections. How do we solve this?
You could do integrating factors.
Yeah, and I think we must, right? Because this is not a separable equation. We would rewrite this as dA dt plus A over 100 equals 6 and use integrating factors. And then once you've solved the ODE, you would use this initial condition to find the missing constant. I implore you guys to do this. I do have the answer here, so I'd like to go ahead and give that to you. You should find that the function A of t is equal to 600 minus 550 e to the negative t over 100. That should be your solution function after you solve the ODE and then use the initial condition to find the constant. All right. So I promise this is one of very few days where I'm going to sit down and talk to you a bunch about applications. These are some classic application problems. Other classic, really important application problems are analyzing circuits. But since so few of us have taken the necessary physics to really understand that, I don't think it's worth doing in this class. One other really important application are logistic equations. That's where you have the population growth, which starts out with this sort of exponential proportional thing. But because of some limiting factor, like maybe your land can only hold so many people, it starts to taper off after a while. So I invite you to read the textbook here, especially if you're going into a science or engineering field. It would be wise to read the textbook, to look through some of the problems and to see if any of them apply to the stuff that you're interested in. Those problems would be problems worth solving. I'll tell you that I'll only test you on the examples that we've seen here today. So we'll either be looking at population growth models, that's unrestricted population growth, Newton's law of cooling, or mixing problems. I won't put anything other than that stuff on the test, but there are many other applications that you should familiarize yourself with if you intend to go into any one of those science fields. All right, that's all we had time for today. So next time I'm going to start talking about general linear differential equations of arbitrary order, constant coefficient, or variable coefficient, homogeneous, non-homogeneous, all sorts of good stuff. So get ready. Next time is going to be very theory heavy. If you missed the test, I'll remind you, you need to reach out to me to schedule the makeup. And if you did not miss the test, then I will have your test graded for you no later than next Monday. If you take the makeup, of course, it's going to take longer to get the test graded, so you'll just have to be patient. That is it from me. If you guys want to talk about anything, you come see me in office hours today. Otherwise, I will see you tomorrow morning.
Bye, Professor.
Take care.